In this video, we discuss learning outcome number 2 from lesson 10.1, which is about calculating and interpreting the linear correlation coefficient R. You'll learn 3 methods for finding R. You're going to learn to use one of those 3 methods to either find or compute R. We'll discuss all 3 of them in this video. My hope is that by the end of this video, you'll be able to describe the rationale behind the formula and explain how R describes the relationship between the variation of X and the variation of Y. Now, the linear correlation coefficient R is also known as the Pearson product moment, after Carl Pearson. He is the person who developed this linear correlation coefficient. The linear correlation coefficient measures the strength of the linear correlation or the linear relationship between paired quantitative X and Y values. Now, if we're talking about measuring the strength of that linear correlation between paired quantitative X and Y values in a sample, we use the linear correlation coefficient R. But if we're talking about measuring the same thing, but using population ordered pairs, then we would call that linear correlation coefficient the Greek letter rho. It looks like a P, but it's not a P. It's like actually a lowercase rho. Again, this was developed by Carl Pearson. If you'd like to learn more about him, you can click this link here, or you can click on his picture. Either of those links will take you to the Wikipedia article about him. And if you follow this link here, you'll find the history of the development of the linear correlation coefficient. Now, one thing that I will say is that if you follow that link, they're talking about the linear correlation coefficient rho, not the linear correlation coefficient R. They're using R instead of rho there. So that means that their formula at the very end is slightly different from the formula that we are going to use for the linear correlation coefficient R. So you want to keep that in mind. But I think that the history of the development of this measure of the strength of a linear relationship between values is really helpful and really insightful in helping us to understand those formulas and where they come from. And so we're going to talk a little bit about that history of the development of this measure in the next few slides. My source is at this link. So if you click here, it will take you to the article where I first learned about the history of the development of the linear correlation coefficient. Not R, but rho. So here's some historical background. Pearson wanted to develop a measure of the strength of the linear relationship between paired quantitative X and Y values. And he started with this. And this was his reasoning. If 2 variables are related by a linear equation, then the corresponding z-scores should be the same. And it turned out that he was right in a special case. If 2 variables are related by a linear equation and that linear equation has a positive slope, remember what this z sub x is going to represent. This is the z-score for a particular x value in our data set. And so the way we calculate this is we take the x value, we subtract the mean of the x values, we divide by the standard deviation of that set of x values, and that z sub x is giving us the number of standard deviations that that particular x value is above or below the mean. So let's say you did all of that and you got a z sub x equals 2.0 for that particular x value. If that x value is paired with a y value, and x and y are related by a linear equation with a positive slope, if that x value is 2.0 standard deviations above its mean, we would expect the corresponding y value to also be 2.0 standard deviations above its mean. So in that way, these 2 values would be the same. So if there was evidence of a linear relationship between the x and y values, these 2 values would be the same. That means that we would get a difference of 0 here. This minus this would be 0, and then the index value would be 0. Now that is exactly what he was expecting to happen if he had a positive linear correlation between the variables, or in other words, if that linear equation describing the relationship between x and y had a positive slope. He said, but if that linear equation involving x and y had a negative slope, well, then he wouldn't expect these z scores to be the same, but he might expect them to be opposites of each other. So if this z value is 2 standard deviations above the mean, and it's related to this y value, and there is a negative slope in the equation describing the relationship between x and y, if this one is 2 standard deviations above the mean, he might expect this one to be 2 standard deviations below the mean. So in that way, these values are going to be larger because we're subtracting something negative here. Or even if this one happened to be negative and this one happened to be positive, when we square it, ultimately those differences are going to be positive if there is a negative slope in the linear equation describing the relationship between x and y. So that was his reasoning. He said, it's really not about the particular value of x or the particular value of y itself. It's about how many standard deviations those x-y pairs are, or how many standard deviations the x values are above their means and the y values are above their means, and how those numbers of standard deviations of x and y should be related to each other if x and y have a linear relationship. So that was his reasoning, and that's why he used this to start. But there were a couple of problems with that measure. It was measuring what he wanted it to measure, but it was measuring it in kind of a strange way, a way that he didn't like. So we saw that we'd have an index of 0. This would be equal to 0 if there was a perfect positive linear correlation between the two variables. And it turns out that that index value would be 4 if there was a perfect negative linear correlation between the variables. He didn't want it that way. He wanted it to be a little bit different. He wanted negative correlations to correspond to negative values of rho. Or in other words, he wanted equations describing the relationship between x and y that had negative slopes to correspond to negative values of his index, this linear correlation coefficient. And he wanted positive correlations, or relationships where the equation describing the relationship between x and y have a positive slope, to correspond to positive values of the linear correlation coefficient rho. So it's kind of backwards right now. We have a 0 whenever we have a perfect positive linear correlation, meaning all of those values lie on a line. And the index would give you a 4 if there was a perfect negative linear correlation. And he kind of wanted that flipped. He wanted this one to be 4 and this one to be 0, but then he didn't really want the range of values of this index to go between 0 and 4. He actually wanted the range of values of his linear correlation coefficient to range from -1 to 1. So this is what he did. If you've ever taken pre-calculus or college algebra, you know that we can use transformations of functions to stretch graphs and change their shape a little bit without changing like the major characteristics of that graph. For example, if you took y equals x squared and you multiplied by 2, that's going to make it twice as tall. Or if you take y equals x squared and you multiply it by 1/2, that's going to make it half as tall. If you add 1 to it, it just moves the whole graph up 1 unit, and so on. All of those things are true. Well, he used transformations of functions to turn his original index into the value we use today. He said, okay, here's my index. I want low values to correspond to negative correlations and high values to correspond to positive correlations. So rather than using this, which is what he originally used, he multiplied it by -1 on the outside to flip that order. And then he said, okay, the values are all between 0 and 4, and I don't want them to be between 0 and 4. I want r equals 0 to imply that there's no correlation, or rho equals 0 to imply that there's no correlation. So let's take that interval from 0 to 4 and shift it so that it goes from -2 to 2. In order to do that, he added 2 to that function. And remember, he's already multiplied it by -1. And then by adding 2 to that function, he shifted that whole graph so that the range of values was between -2 and 2. And then he said, I don't want the values to go from -2 to 2. I want them to go from -1 to 1. So he took the whole equation and he multiplied it by 1/2. 1/2 of 2 is this 1. And then we have the -1/2 here times the original index that he started with. Now, if you do a bunch of algebra, you can show that this right here simplifies to this. What we end up with is a sum of the products of the z-scores for the x value and the corresponding y value in each ordered pair, divided by the sample size, or excuse me, the population size for the entire population. That is giving us the linear correlation coefficient rho for the population. Now, in practice, if we're using sample data, rather than dividing by that sample size n, we're going to divide by 1 less than the sample size, n minus 1, in order to get our linear correlation coefficient r. So that is where it comes from. That's why we're using z-scores here, because z-scores are measuring a number of standard deviations above or below the mean. And if the x, y values line up on a straight line, and that line has a positive slope, then these two values, the z-score corresponding to the x value and the z-score corresponding to the y value, they're going to be very similar. So when you multiply those together, you're going to get a positive result. And if they both happen to be negative, you're going to multiply those together and you're going to get a positive result. If you do that for all of the x, y pairs and you divide by n minus 1, you're going to get your r value. Now, if all of the data values are sort of all over the place so that there isn't a relationship between x and y, sometimes when you multiply these together, you're going to get positive values. Sometimes when you multiply those together, you're going to get negative values. And when you add them all together, you're going to get something close to 0. That's what happens to this r value when x and y are not correlated in a linear fashion. So that's where that comes from, and that's why we use the z-scores. Now in practice, it's kind of computationally intensive to find the z-scores for every x value and every y value, multiply those together, add them, and then divide by the sample size minus 1. It's a very simple formula, but it's a little bit misleading because there's a lot of computation that goes into it. So in practice, we don't tend to use this unless we're trying to emphasize our understanding of this formula, the fact that we're actually taking the z-scores, which is a number of standard deviations above or below the mean. We're adding those, we're multiplying them, then we're adding them together, and we're dividing by the sample size minus 1. Now, when we're trying to interpret these r values, remember the r value is used to measure the strength of the linear association or relationship between the two variables. So on this first picture, in picture A here, we see a graph of paired data, and it looks approximately linear. As x increases, y increases. I could imagine drawing a line through all of those data, and that line would have a positive slope. So this is a positive correlation, or would indicate a positive correlation. And if we compute r, the formulas would give us 0.859. Now over here, we notice that these data also line up in a line, but since as we go from left to right, as x increases, the y values decrease, so the slope is negative. This is exhibiting what's called a negative correlation. So r is approximately negative 0.971. Notice how these are closer to their sort of center line or best fit line than these points are. And the value of this r value over here, sorry, using the word value too many times. Notice that the absolute value of this r is very close to 1, and the absolute value of this r is close to 1, but it's less close to 1 than this one is. That's no mistake. If r is equal to -1, that means x and y lie on a line and that line has a negative slope. If r is equal to +1, that means x and y, all those xy pairs lie on a line and that line has a positive slope. Now, if they don't all lie on a line, but they lie close to a line, like this data or this data, you're going to have different values of r. The r values are always between -1 and 1. And the closer that those r values get to those extremes, of getting close to 1 or close to -1 on the low end, the closer that data come to getting just lying on an actual line. So notice the absolute value of r is greater over here than it is over here because these points are closer together than these points, and that makes sense. That's consistent with what we know about this linear correlation coefficient r. Now, if there's no correlation, what you're going to see is a scatter plot like this. There are dots all over the place. There's no line that would best fit through all of that data. And then in this last graph here, we see a relationship, but it's not a linear relationship. That looks like all of those points are lying on a parabola. Here, the r value is 0.330. And we would say we do have a relationship, so we do have a correlation, but it's a nonlinear correlation, not a linear correlation. So the r value is low. It's close to 0. Notice that the r value for no correlation is very close to 0. R equals 0.074. Now, as I mentioned earlier, lowercase r is being used to represent the linear correlation coefficient for paired sample data, and lowercase rho is the linear correlation coefficient for paired population data. Now, when we use our formulas that are coming up, the lowercase n represents the number of pairs of sample data. So it's the number of ordered pairs we have. It's not the number of values that we have. That sigma denotes the addition of the items in front of it. So if we see sigma sub x, that means the sum of the x values. If we see sigma with an x squared in front of it, that means that we should take each x value, square them, and then add them together. And then notice that this one looks just like that one, almost, but this says add the x's first and then square it. Be very careful. This one means you square the x's and then add. This one means you add the x's and then square them. They're two different things. And of course, we could have y's here instead of x's, and that would be fine too. Those appear in our formulas as well. And this is a sum of x times y. That means each x value should be multiplied by the corresponding y value. And then after you multiply the x and y values together, you add them together to find the sum of those products. So this is the formula that we just looked at. This is a good formula for understanding. So it says, take the number of standard deviations each x value is above or below the mean. That's its corresponding z-score. And do the same thing with the y values. Multiply those together. Add them and then divide by the sample size minus 1. That is one way that you can measure the strength of that linear correlation between the x values and the y values. Another way is to use this formula. Now, I know this formula looks a mess. It looks hard, but it's actually much better for calculations than formula 10-2. This was the formula that was used for hand calculations before we had all of the technology that we have today. Someone said, okay, yes, we can come up with these z-scores, which are often numbers between approximately -3 and 3 most of the time, right? And then we would have a number of decimal places. So you'd have some decimal here and some decimal here. You'd have to multiply those together and then add and then divide by this n-1. Well, if your x and y are small integers or numbers that are really easy to work with, it's much easier to just add all the x's, add all the y's, take the x's and y's and add them, or multiply them and then add the results. Take the x's, square them, and then add them. Take the y's, square them, and then add them, and then just substitute everything into this formula. So even though this looks more intimidating, it's actually much easier to compute by hand than that formula that was on the last slide would be as far as ease is concerned. I'm sorry, I'm just not feeling very well tonight. But this is computationally easier than the last one, and that's how it was used historically. Um, so we would use this formula for calculations rather than the formula 10.2, which was on the first slide. I showed you formula 10.2 before I showed you formula 10.1 because 10.2 implies what R is all about. And formula 10.1 is algebraically equivalent to formula 10.2. It's just easier to work with when you have the X and Y values right in front of you. Now, when you compute these R values, we want to round to 3 decimal places, because we're going to take the R value and then compare them to the critical values of R from table A5 in the Triola formulas and tables. And that's why we round to 3 decimal places, so that it's easier to compare. Now we have some requirements, and these are requirements for testing a claim of a linear correlation between the two variables. Now, if you have any collection of paired sample quantitative data, we can compute that linear correlation coefficient R, but it's not always meaningful. We want the following requirements to be met if we want to use that linear correlation coefficient R to test a claim about correlation between one variable X and a second variable Y, where X and Y are both quantitative data. And here are those requirements. First, we need a simple random sample of quantitative data. Next, a visual examination of the scatter plot should confirm that the points approximate a straight line pattern. If the points look like they lie on a parabola or on an exponential function, we could compute R, but it would not be meaningful because the data don't actually lie on anything resembling a straight line. So we should see that a straight line pattern is appropriate before computing R and then using R to interpret or using R to decide whether there's a correlation between the variables. And then because results can be strongly affected by the presence of outliers, as can be seen from that first formula, which deals with the number of standard deviations a particular value is above or below the mean. Any outliers that are known to be errors must be removed so that, or before we calculate R. Now, if you have any outliers and they're not known to be errors, we should consider those separately. We should compute R with and without the outliers and make decisions based on the two values of R that we get in those cases. The second and third requirements here, this visual examination that shows us that our scatter plot resembles data lying close to a straight line. And that third requirement that says that we should remove the outliers if we know them to be errors, or otherwise calculate R with and without the outliers. Those are allowing us to imply that the pairs of XY data that we have a bivariate normal distribution. And all that means is that if the X value is fixed, the corresponding Y value that is paired with it would have a normal distribution. Or if one of the Y values was fixed, the corresponding X value would have a normal distribution. So that means the X values are approximately normal, the Y values are approximately normal, and they're approximately normal when one of the variables is held constant and the other one is allowed to vary. That's actually really hard to check. So rather than checking that, we're going to check requirements 2 and 3. So we're just going to see, does it look like it lies along a straight line? Do we have any outliers that might strongly affect the value of R? If so, we should remove those. Now here are some properties of the linear correlation coefficient R. The value of R is always between -1 and 1 inclusive. Or in other words, R is between -1 and 1, and R can equal -1 or R can equal +1. Second property is that if all values of either variable are converted to a different scale, the value of R doesn't change. And I think that's pretty obvious when you look at this formula over here, our first formula, which is being denoted by formula 10.2 in our textbook. I think you can tell that changing the scale shouldn't change the value of R, because changing the scale won't actually change the number of standard deviations that particular X value is, or that particular Y value is, or above or below the mean. So the z-scores are going to remain constant even as we change to different scales. So you can change either variable to a different scale and your correlation coefficient will not change. Because again, this is based on the z-scores of the data values, not the units used or the values of the X or Y themselves. Third, the value of R is not affected by the choice of X or Y. If you switch all the X values and the Y values, the value of R will not change. And I think that's obvious from this formula, because we could easily swap out Z sub X and Z sub Y, and we would have the same product right here in the numerator. Fourth, it's important to remember that R measures the strength of a linear relationship. It's not designed to measure the strength of a relationship that's nonlinear, like a parabolic relationship, or a relationship where one variable is exponentially related to the other. If the relationship's not linear, we can compute R, but it won't necessarily measure what you're hoping it will measure. It's not measuring correlation in general, it's measuring the strength of a linear correlation. So make sure you don't interpret R incorrectly when your scatter plot might indicate that the correlation exists, but it's nonlinear. And 5, R is very sensitive to outliers, again, because of the presence of these z-scores. If we have an outlier for X or for Y, or even an ordered pair X and Y, those z-scores are going to be very high or very low. Those are going to be a large number of standard deviations above or below the mean. So that's going to affect that quotient quite a bit. It's going to change the value of R quite a bit. So we need to be careful about including outliers. If we choose to include them, we should calculate R with and without them, and then decide based on those results what to do with the outliers. Okay, so there are actually 3 methods that we can use to find R, and we've already talked about 2 of them. We have 2 formulas. The first method, though, that I would recommend you use is to use technology. We're going to use Excel's Pearson function, and I'll show you how to do that very shortly. You can also use formula 10(1). Now that is the longer formula involving the sum of the x's, the sum of the y's, the sum of the x's times y's, the sum of the x's squared, the sum of the y's squared, and all of that. Even though it looks like it's a lot, it's actually computationally simpler. It only involves computing values of x, y, x squared, y squared, and x times y, and then adding those together and then substituting into a formula. If x and y are integer values or small values, that is relatively simple to compute all of that, and easy to do by hand. So formula 10(1) is the one that you should use if you want to compute R by hand, as we'll see shortly in this video. Sorry, I'm just not feeling well tonight. Then the third method for computing the value of R is to use formula 10(2). Now, this does require more computation, but the advantage of using formula 10(2) is that it enhances our understanding of what we're doing and why we're doing it. It takes each X value and each Y value and it translates it into the number of standard deviations that X or Y value is above the mean. And then we take those products and we add them together and we divide by the sample size minus 1. And that gives us an accurate measure of the strength of that relationship between X and Y. So you can use formula 10(2) if you want to emphasize what it is you're doing and why you're doing it. So we're going to use technology in this first example. We've got 5 paired data values, and we want to find the value of the correlation coefficient R for the data. We have an amount of chocolate consumed, and I forget what the units are on this data. And then we have the number of Nobel laureates in each of these countries. So this 5, 6, 4, 4, and 5 is some number of units of chocolate consumed, I believe, per capita in those countries. And these are the number of Nobel laureates that they have in each country. We want to know, is there a correlation between chocolate consumption in a particular country and the number of Nobel laureates they have in that country? Well, we could use technology to answer that question. In order to do that, I would list the data in 2 columns in an Excel spreadsheet, and then I will use the Pearson function, as I mentioned. So let me show you how to do that in Excel now. So this is actually very simple. To compute the correlation coefficient R, I type equals, and then I type Pearson, and that's the name of the person who developed this Pearson correlation coefficient. And this is asking for 2 values, 2 arrays as arguments. The first array is your set of X values. So we would select all the values for the chocolates and then type a comma, and then you want a second array for the set of Y values. Then close parentheses, and then you get that there. If we want to round to 3 decimal places, we get 0.795. That is the value of our correlation coefficient R using Excel. Easy. It's just equals Pearson, select the X's, select the Y's, close parentheses. Now, the value of R can also be calculated with calculators like the TI-83 or 84 or software. If the data is entered into the calculator or software correctly and then referenced correctly, as long as you enter it correctly, the software packages will tend to just spit out the value of R. So let me show you what you would see. If you use a TI-83 or 84 plus, the R value would show up where you look for the linear regression t-test. And you'd see the R value down here. That's 0.79449, which is the same R value that we got using Excel. Now you can use StatDisk. The output will look like this. You can use Minitab. The output will look like this. StatCrunch gives you this output. Excel's Stat, that's for Excel. The statistics package that you can actually download to your Excel program. And it gives you this little output here. It's correlation matrix. That value there is the correlation between chocolate and the Nobel data, Nobel laureate data. And 1, 2, 3, 4, 5 programs, all of them have that 0.7949. So they're all just giving you that value of R, provided that you are entering your data correctly. And if we round, we have 0.795, which is the same value that we got using Excel. So that's one way of doing it, and I highly recommend that you use that method as you're doing your homework. But it's good to be able to compute things by hand as well. So we could compute R using formula 10-1 if we wanted to as well. And that requires finding a lot of different columns of values. We have to use this formula. So we're going to take the X's and Y's, multiply them together and add. We're going to add all the X's, we'll add all the Y's. We'll take the X's, we'll square them, and then we'll add them. We'll take the Y's, we'll square them, and then we'll add them. That's the plan. And then N is the number of ordered pairs we have. We have 1, 2, 3, 4, 5 ordered pairs. So N equals 5. We would substitute that into our formula as well. So usually when I'm doing this, I count, I find out how many pairs of ordered, or how many ordered pairs of data that we have, which is N equals 5. And then we'll create columns for the squared variables and the product X times Y. So I've got this, I'm just listing my X values in a column, my Y values in a column. Then I list X squared here, Y squared here, and X times Y here. And then down here at the bottom, I know I'm going to sum all of those. Let's actually do that together. In order to do that, I will share my paper with you. So I want the x's squared in one column. I want the y's squared in another column. And I want x times y in another column. So this is historically what would be done. If they have the xy pairs, they would just do this computation by hand. So I'll take my x's and square them. 5 squared is 25, 6 squared is 36, 4 squared is 16, 4 squared is 16, 5 squared is 25. Then we'll square the y's. So 6 squared is 36, 9 squared is 81, 3 squared is 9, 2 squared is 4, and 11 squared is 121. And we'll take x and y and multiply them. So I have 30. Here, multiply those together, we get 54. 4 times 3 is 12. 4 times 4 times 2 is 8. And 5 times 11 is 55. And then in each of these columns, we want to add them together. Now you could do that arithmetic in your head as well, but I'm going to use my calculator to make this faster. 5 plus 6 plus 4 plus 4 plus 5 is 24. And then we have 6 plus 9 plus 3 plus 2 plus 11 is 31. Then when we add these guys together, 25 plus 36 plus 16 plus 16 plus 25 is 118. Then we have 36 plus 81 plus 9 plus 4 plus 121. And then we have 30 plus 54 plus 12 plus 8 plus 55. Okay, now these are values that we need in our formula for R. So R is given by this. It was n times the sum of the x's times the y's minus the sum of the x's times the sum of the y's, all divided by the square root of n times the sum of the x's squared minus the sum of the x's squared times the square root of n times the sum of the y's squared minus the sum of the y's squared. Sample size is 5. That's the number of ordered pairs we have. So we'll have 5 times the sum of the x's times y's, which is 159, minus the sum of the x's, which is 24, times the sum of the y's, which is 31, all divided by this. Now, there's a property from algebra that I want to use here. The square root of a times the square root of b is the square root of a times b. That's what I'm using here. And please don't be distracted. This is for another class. Over here, n is 5. The sum of the x's squared is 118. And then the sum of the x's squared is 24. And we're going to square that. All of that is multiplying all of this. N is 5. The sum of the y's squared is 251. Then we want the sum of the y's, which is 31, and we want to square that. So if I use my calculator for this arithmetic, I have 5 times 159, 5 times 159, not plus 159, minus 24 times 31 is 51 in the numerator. And then I have 5 times 118 minus 24 squared is 14. And then I have 5 times 251 minus 31 squared, which is 294. So I want 51 divided by the square root of 14 times 294, which is approximately 0.7949, which is the same value that we got using Excel and using all of the other types of technology. Okay, so that's one way of doing it, just using that formula. Okay, so we fill in the table, and let me see, I got 24, 31, 118, 251, and 159. That's the same thing I got on my paper. That's good. And we substitute everything into the formula, and we get the same thing, approximately 0.795. Okay, Now we can use formula 10.2 as well to find the value of the linear correlation coefficient R. And we'll still get that 0.795, but here we want to emphasize that we're taking z-scores for each x value and for each y value. And then we're multiplying those together, we're adding them, and we're dividing by 1 minus the sample size. No, the sample size minus 1, sorry. We want to emphasize that these are products of z-scores, and that is what is allowing us to measure whether or not those points lie on a straight line. So we're going to use this formula, but that requires a little bit more work. So let's talk through how that would work. First, we're going to use technology to compute the mean of the x values, the mean of the y values, the sample standard deviation for the x values, and the sample standard deviation for the y values. Once we do that, we're going to use these formulas in order to compute the corresponding z-scores for the x's and y's for each value on our list. Then we're going to multiply those together, add them together, and then divide by 1 less than the sample size. So for example, if we're using unrounded numbers, the chocolate values have a mean of 4.8 and a standard deviation of approximately 0.836660. So our first chocolate value of 5 would be converted to a z-score using this formula, and that's approximately 0.239046. You're going to do that for all 5 of those values. You can see why this is computationally intensive. You've got to compute this, and then you've got to do this for all of the x values, all of the y values, multiply, then add, and then divide by n minus 1. It's a lot. But then at least you know that that chocolate value of 5 is 0.24 standard deviations above the mean. And you can think about that. You can think about that value of 5 is 0.24 standard deviations above the mean, and look at the corresponding y value and see what happens when we multiply those z-scores for the chocolate and the z-scores for the number of Nobel laureates, and how that appears in our formula. So that's the plan. That's what we're going to do. And that turns out to give us something that looks like this. Now let's do all of that in Excel. Okay, so in Excel, these are my x values, and these are my y, the Nobel laureates are my y values. So actually, I think I want to insert a column. And I will put the sample mean here, this first row, and I want the sample standard deviation in the second row. Now the command in Excel for each of those is average. So we take the average of those values, we type equals average, open parentheses, we highlight the cells, drag and drop, close parentheses. That gives me that mean of 4.8, which was mentioned. And then I also want the sample standard deviation. So I'll type equals ST, and then you see stdev.s. That's the one we want. That .s means sample standard deviation as opposed to population standard deviation. Remember, they're a little bit different. One has the sample size -1 in the denominator. The other one has the true population size. There's no -1. So we need the one that has the S for the sample standard deviation. Open parentheses, and then select the values on your list for the X's. Oops, don't include that mean. We don't want that. Close parentheses, and we get the same value that they had in Excel, or sorry, in the slides. I said they had the same value that we had in our slides. Okay, now let's compute the mean for the Nobel laureates. So we'll type equals average, open parentheses, highlight these, close parentheses, and then we'll type equals stdev.s, open parentheses, highlight these, close parentheses. So now we have a mean and a sample standard deviation for every x value. Now I want the z sub x's right here. So that's going to require me to take this x value and subtract the sample mean and divide by the sample standard deviation. Now it did that correctly, but I think I need to put a dollar sign in here somewhere. I think it's $7 and $8. If I want to drag and drop, but I don't want to change the B7 or the B8. I think putting that dollar sign in the middle actually effectively does that. So let's drag and drop and see if it gives me what I want. This is B2 minus B7 over B8. This is B3 minus B7 over B8. Excellent. That's exactly what I wanted for my Z sub x's. Those are the z-scores corresponding to my x values. Here I want the same thing, but I want the z-scores corresponding to my y values. So I will type equals, open parentheses, I want my y value. I want to subtract the sample mean for the y values, and I want to divide by the sample standard deviation for the y values. That's right. But then I want to go in, I want to add a little dollar sign. So that's C7 and C8 with a dollar sign in between. And that's going to make sure we continue to reference C7 and C8 as we drag and drop. So notice this one is C3 minus C7 over C8. This one's C4 minus C7, all divided by C8, and so on. So the first x value is 0.24 standard deviations above the mean. The corresponding y value is negative 0.05 standard deviations. That's the number of standard deviations below the mean for the y values. Then we want to take the product of those, numbers of standard deviations above and below the mean. So we're taking that, and we're multiplying that. Drag and drop. And then we want to add all of those together. So I'll type equals sum, open parentheses, and I'll select all of the values I want to add. And then my correlation coefficient, R, was equal to this using the built-in Pearson function. Without using the built-in Pearson function, I want to type equals. I want to take that product, and I want to divide by the sample size minus 1. There are 5 ordered pairs, so the sample size minus 1 is 4. And I have 0.795 when I round to 3 decimal places as well. So that's using formula 10.2. And the reason we might use formula 10.2 is in order to see those numbers of standard deviations, each of those values is above the mean. This 4 and this 2, for example, this 4 is about 0.96 standard deviations below the mean. The 2 is about negative 1.1 standard deviations below the mean. I don't know if I said above or below there. They're both below their means. When you multiply them together, you get this positive value here. So when you multiply these guys together and you get a positive number over here, that tells you, that they're in the same sort of quadrant. I've got 2 z-scores that are below their means. When I multiply them, I get something that is positive. Here I've got 2 z-scores corresponding to x values and y values that are above their means. When we multiply those together, we get a positive product. The only time we don't get a positive product, the only time we get a negative product is when you have one that is a number of standard deviations above the mean and the other one that is a number of standard deviations below the mean. And that we only had that happen once with this first ordered pair. And notice that the magnitudes of those z-scores were pretty low to begin with. So when you multiplied them together, you got this negative 0.01. So it's taking away from that R value the fact that this z-score is positive when this z-score is negative, but it's not taking away very much because these z-scores were both so close to 0. Okay, so I hope that helps you understand not just how to use the formulas, but understand where these values come from. Let's keep looking at our slides. And we see we get the same value using that. And the last thing that I'd like to talk about in this video is how we interpret R. It turns out that the value of R squared is the proportion of the variation in Y. That's how much Y varies from its mean. That is explained by the linear relationship between X and Y. So it's saying how much the variation in Y actually depends on the X value. R squared is that value. That's how much, that's that proportion of the variation in Y that's explained by the relationship between X and Y. So for example, we looked at 5 ordered pairs of Nobel chocolate data, but if we looked at 23 pairs of chocolate data and Nobel Prize winners, Nobel laureates, it turns out that the R value that you get for that is 0.801. The question says, what proportion of the variation in the numbers of Nobel laureates can be explained by the variation in the consumption of chocolate? If you take that R value of 0.801 and you square it, you get 0.642. And what that means is that 0.642, or 64% approximately, of the variation in the number of Nobel laureates can be explained by the linear relationship between chocolate consumption and the number of Nobel laureates. So we're saying there are a lot of things that will contribute to the number of Nobel laureates that a country has. But 64% of that variation in the number of Nobel laureates can be explained by how much chocolate that country tends to consume. But that also means that 36% of that variation is not explained by chocolate consumption. So there's something else that is affecting the number of Nobel laureates that a particular country has. And that 36% of that variation comes from some other variable or variables likely that explains the variation in the number of Nobel laureates in those countries. So that is the end of our discussion of the linear correlation coefficient R. I'm sorry that I'm not feeling 100%, I'm not feeling my best. Please let me know if you have any questions about this material. I will probably be making another version of this video in a future semester when I'm feeling a little bit better. Yeah, if there's any part of that that was unclear because I'm sort of sick, let me know, and I'll be happy to go over it again with you, hopefully when I'm feeling a bit better myself. So that's the end of this video about the linear correlation coefficient for sample data R. In the next video, we'll discuss conducting a hypothesis test to determine whether there is a linear correlation between 2 variables using the critical value method.